Hello learners, Mr. G here, and we are going to be making a video on work, energy and power. Generally this question will have a little bit of everything. It will have something about momentum, it will have energy, and it will have something about Newton's law as well. This was question 5 from September 2015 in the Northern Cape province. So let's read the question quickly so we can start with the answer as fast as we can. Say a block of mass 6 kilograms slides to the right with a constant velocity of 8 meters per second on a horizontal frictionless surface. It collides with a stationary block of mass 5 kilograms. The blocks move together to the right as a single system along the same surface. Refer to the diagram below. So we have this one here. The block of 5 kilograms is stationary, so the velocity here is equal to 0. That is important data we are going to go, and then they're going to stack together and move together as a unit. Okay, now at 5.1 state the law of conservation of linear momentum in work, and 5.2 calculate the velocity of the system of the blocks immediately after the collisions. So let's go to the solution. The question is a little bit long, but we're going to do it slow. So solution question 5.1 is the law of conservation of momentum. So the principle of conservation of linear momentum states that the total linear momentum of an isolated system remains constant. Very important is the word total. You cannot forget to write the word total here, or isolated system. This is 2 marks, and then you will get 2 marks if you state the law. Alright, question 5.2. Say calculate the velocity of the system of the 2 blocks immediately after the collision. Remember, this area here is frictionless. The frictional force is equal to 0. There is not friction on that area before they bump each other and continue moving. So we have to use the law or the principle of conservation of linear momentum here in this question 5.2. Now we're going to start saying by the total linear momentum initial is equal to the total linear momentum final. Alright, now we have 2 objects here. So this one is the initial momentum of object A or block A plus the initial momentum of block B is equal to the final momentum of block A plus the final momentum of block B. Alright, now this object is moving all the time to the right. So right is going to be positive. That direction is going to be a positive. You don't have to write that if you don't want to. And remember that momentum is equal to mass multiplied by velocity. This is the definition of momentum, and it is in the formula sheet they give you at the end of the question paper. Okay, so we have here that the mass of object A multiplied by the initial velocity of object A plus the mass of object B multiplied by the initial velocity of object B is equal to mass of object A multiplied by the final velocity of object A plus mass of object B multiplied by the final velocity of object B. Now something important here. The objects are moving together. The objects are moving together after they bump each other. So they will have the same final velocity, which I'm going to calculate to write the velocity of the system, final velocity of the system, and then the masses you can add because they are a common factor. So this is mass A plus mass B. Do not start from this point. This one, start from here, because if you do that, then any of this formula you did right there will give you 1 mark, but not all the time you have the object that move together after they bump each other. So what we have here, we have that the mass of object A multiplied by the initial velocity of object A plus mass of object B multiplied by the initial velocity of object B is equal to velocity final of the system. Those are the 2 blocks. That is what we are looking for, multiplied by mass A plus mass B. So let's now do the numerical substitution here. What we have? What is mass of object A is 6. The initial velocity is 8 meters per second, plus mass of object B is 5. The initial velocity is 0, it is at rest, is equal to final velocity of the system. You are looking for that one, multiplied by 6 plus 5. And when you do the calculations here, which I am not going to be doing all the calculations, otherwise it's going to take too long, the final velocity of the system is going to be equal to 4,36 meters per second to the right. To the right. Now, important that part. The question here, let's go back to the question. The question says calculate the velocity. Velocity is a vector quantity, so you must give the direction. So the marks allocation here are 1 mark for any of those formulas there, 1 mark for the substitution on the left hand side in which the 5 times 0 doesn't need to be there, 1 mark for the substitution on this side here, and 1 final mark for the calculation, the final solution with the direction. So it's 4 marks for this specific question. Let's go, I hope it's understood. Let's go to question 5.3. Now, in this question, we have a new situation. Say the block system continue moving with the same common velocity of point A. So the point A, the velocity at point A, the velocity here of both of them is going to be the one you just calculated, of 4,36 meters per second. That one was calculated right now. Okay, and they say then continue over the rough section AB, a distance of 2 meters passing point B at 1,5 meters per second, and the velocity here is equal to 1,5 meters per second. So we have an initial velocity here of 4,36 and we have one final velocity here of 1,5 meters per second. They are giving you that the distance is 2 meters only for that section AB. Okay, the system continues up the rough ramp, finally coming to stop after moving a distance of a d. So here, distance d, this velocity here is going to be equal to 0 because the two blocks just stop there. Okay, but now the question is for A and B. So let's go to 5.3. Use energy consideration only to calculate the coefficient of a sliding friction between the block system and the surface over the 2 meter stretch. Now, they say only use energy consideration. Therefore, the word only, that you cannot use now Newton's law or other way of calculating. However, remember that frictional force is equal to the kinetic coefficient of friction multiplied by normal. Alright, so you don't have to use Newton's law, but you need to use this formula because it's the formula to calculate the coefficient of kinetic friction. Most definitely you need some point that formula in which you are going to some point need the frictional force and you are going to need the normal force. Alright, so 5.3. The first thing we're going to do is to draw the free body diagram. This is not related to Newton's law, it's related to any question in physics and mechanics. Okay, so what forces are acting on that object? We have here that the forces acting are going to be the frictional force. Remember, there is not a force being pulling the object down. The object was just moving forward. We have the normal force and we have the weight. And without carry on here, without using Newton's law, you can see that in the y-axis, the only two forces are these two forces here. They are balanced, they are at equilibrium, so the normal force will be equal to weight, and it's going to be equal to mass multiplied by acceleration due to gravity. This one is important because you may need it in the formula. Remember, you need the formula of frictional force. Okay. Sorry. So now we have to get the frictional force, and they say we can only use energy consideration. So how can we calculate the frictional force? Well, the work done by the frictional force is equal to frictional force multiplied by the displacement, which we know is 2 meters, multiplied by the cosine of theta, which is 180 180 degrees for the frictional force. So this is a way we can use. However, we don't have the work done by friction, but we can use the work energy theorem to calculate the work done by friction. So we are going to apply the work energy theorem to calculate the work done by friction. The work energy theorem states that the work done, the net work, or the work done by the net force, is going to be equal to the change in kinetic energy. What are the forces acting on the object that that actually does work, because normal doesn't do work and weight does not do work in these cases here? Okay, so what forces we have? Only the work done by frictional force, and this is equal to half mass final speed square minus half mass initial speed square. So the work done by frictional force, we can substitute the formula there, and we have that frictional force multiplied by displacement multiplied by the cosine of 180 degrees is going to be equal to half mass final velocity or speed square minus half mass initial speed square. And this is the way that we can use to calculate the frictional force. Let's then substitute everything that we have here. Everything that we have here. If you want, you can even substitute the formula for friction that we wrote right there in the question. Let me just show you. There is the formula, kinetic coefficient of friction multiplied by normal. So if you want, you don't have to. If you want, you can substitute here already that formula there. Remember, frictional force is equal to kinetic coefficient of friction multiplied by normal. If you want, you can substitute it. In fact, let's substitute it there because it's quite easy. So instead of writing frictional force, we are going to write there. Instead of writing frictional force, we are going to write kinetic coefficient of friction multiplied by normal multiplied by displacement. Note, all this is just friction. You can see the formula multiplied by cosine of 180 degrees is equal to half mass final speed square minus half mass initial speed square. And normal, if you want, you can still substitute normal. It is here in the free body diagram. Normal is going to be equal to weight. So you can say here that kinetic coefficient of friction, no, normal is equal to weight in this situation. It's not always going to be like that. Okay, so kinetic coefficient of friction multiplied by normal, but normal is going to be mass multiplied by acceleration due to gravity multiplied by displacement multiplied by cosine of 180 degrees is equal to half mass final speed square minus half mass initial speed square. And then you can substitute all the numerical values here. So let's substitute all the numerical values. We have the kinetic coefficient of friction multiplied by normal, by mass. Remember the mass of both objects because they're moving together. So it's going to be 11. Mass is 11 because it's mass A plus mass B. Remember, they are moving together. Multiplied by 9,8 multiplied by the displacement, which is 2, multiplied by cosine of 180. I'm going to leave it. So if you want, you can write multiplied by minus 1 equal to half multiplied by 11. Remember, the speed, the mass is together. The final speed is at the bottom of the ramp, 1,5 to the power 2 minus half 11, which is the mass, 11 multiplied by the initial speed, which is the one you just calculated in the previous question, 4,36, everything to the power 2. And then that is all. You can then just calculate for kinetic coefficient of friction, and this one is going to be, when you do the calculations, please redo the calculations, okay? 0,43. This is the answer for this specific question. The marks allocation are 1 mark for any of this one here. Any of that one will carry 1 mark. 1 mark for the whole substitution on the left hand side, 1 mark for the whole substitution on the right hand side, and 1 mark for the final answer. Okay, so that is the mark. Yes, in this question there is an extra mark. In this question was an extra mark just for the starting point, work energy theorem, and then 1 mark for any of this one here. Those are 5 marks for that question. I hope you understand. It's not that bad. Okay, so let's go to question 5.4. Question 5.4 say the system of the two blocks light up the ramp with the same coefficient of friction. So the coefficient of friction is the same coefficient of friction, the one we just calculated. Sorry, what happened there? Sorry about that. Same coefficient of friction. So it was the same one as we calculate. Okay, what is happening here? Sorry, I'm not quite sure. Let me see. Same coefficient of friction. There we go. But why? Here we are. Sorry about that. The same coefficient of friction. Use Newton's law. Now you do have to use Newton's law. You cannot use anything else. You cannot use energy now of motion to calculate the distance d. So now what we have here, 5.4. Okay, as we always do, we're going to do the free body diagram, and in this case the object is moving up the ramp. Now, important to know, the x-axis is going to be always parallel to the surface. So this is like the ramp. The x-axis is like the incline. Okay, so what forces are acting there? Okay, there is friction. Remember, the friction with the same coefficient of friction doesn't mean the same friction, it means the same coefficient of friction. This is frictional force. There is normal force perpendicular to the surface, and there is weight always pointing down. Now, weight is not in any of the axes, so we must determine the component. It has a component in the y and it has a component in the x, and this one here is the angle of inclination, which is 30 degrees. Okay, now what forces are there? The components will be on the y-axis. There is going to be weight in the y-axis, which is equal to weight multiplied by cosine of 30 degrees. And here on the x you will have weight, let's just write it here, weight in the x-axis, which is equal to weight multiplied by sine of theta. So that is important thing because we are going to use it now. Okay, now what Newton's law we are going to use here? We are going to use Newton's second law. Now Newton's second law, the formula will be F net equal to mass multiplied by acceleration. Okay, there is an acceleration acting on that object. Okay, which is what we will need eventually to calculate the acceleration. This question is a little bit tricky. Now, what forces are acting? We're going to work in the x-axis. I am going to write here in x-axis first, because there is where the object is actually moving. Okay, in x-axis. So what forces do we have? Remember, we take the direction in which the object moves as positive. So up the ramp is positive, therefore the friction and the component of the weight in the x-axis are both negative. So will be minus frictional force minus weight in x equal to ma. We have the weight in x. There is the formula for weight in x, so we can substitute it in here, and let's do so. We have minus frictional force minus weight in x, which is equal to weight multiplied by sine theta is equal to ma. Now weight, we can even go further and say that weight is equal to mass multiplied by acceleration due to gravity. So it's minus frictional force minus mass multiplied by acceleration due to gravity multiplied by sine of theta is equal to ma. Now we still don't have frictional force. So frictional force, remember, from the previous question, frictional force here is going to be equal to kinetic coefficient of friction, which we did calculate, multiplied by normal, and the normal here is a different one, okay? But let's substitute that formula first there, okay? So what we have, minus kinetic coefficient of friction multiplied by normal minus mg sine theta is equal to ma. I hope up until here is not problems. Now, normal force. We don't have normal. Normal, we have to come back here to the axis, is in the y-axis, and you can see the only forces are normal and the weight in the y-axis. Those are the only two forces in y. The forces in y here are balanced. So the normal force here, in actual fact, you're supposed to use Newton's first law here, okay? But we are going to just say that normal is going to be equal to weight in the y-axis, okay? And weight in the y-axis is there. All right, so here we have that minus kinetic coefficient of friction multiplied by normal, but normal is going to be the weight in the y-axis, minus mg sine theta. Theta is 30. Let's just write the 30 here already, equal to ma. Recalled here, weight in the y-axis is that one there, so it's equal to weight minus kinetic coefficient of friction multiplied by weight multiplied by cosine of m. Let's just move a little bit further. Weight multiplied by cosine of theta, but weight is mg. Now we can say cosine 30 degree minus mg sine 30 degree is equal to ma. And here we have all the information. We can just substitute, and we are going to do so. We have something else that we don't know yet. Remember, we're looking for distance, and in this formula we don't have distance, so we have to go back to a formula where we can calculate distance, but we're going to need the acceleration. So if you substitute here, you'll have the following: minus, I'm going to open bracket because everything is minus here. Minus is for everything, okay? Minus 0.43 multiplied by the mesh, which is 11. Remember, they're still moving together. Multiplied by 9.8 multiplied by the cosine of 30. Minus bracket because it's everything. Remember, this minus is for everything inside the bracket, okay? So let's do this just for no confusion. So we're going to open here minus, and we're going to open another square bracket. The product of 11 multiplied by 9.8 multiplied by sine of 30 degree, and this is going to be equal to 11a. When you do that calculation, acceleration is equal to minus 8.55 meters per second square. That is the acceleration, but we are not looking for acceleration, we're looking for distance. So we have to go back to the formulas in the formula sheet and look for a formula that can help us to calculate the distance. In this case, final velocity square is equal to initial velocity square plus 2 multiplied by acceleration multiplied by the displacement, which it will be the distance here. So if we substitute the final velocity is 0, the initial velocity is the one which started up the ramp, is 1.5 square plus 2 multiplied by negative 8.55 multiplied by the displacement, which is the distance, and then the distance is going to be 0.26. Remember to do all the calculations. I may have mistakes with the calculation. So that is the question 5.4. To me is the most difficult one in this specific question, and the marks allocation here are the following. You get 1 mark for any of this one here, then you get 1 mark for this side here, any of those. Then you get 1 mark for the substitution here and the substitution here. 1 mark for this formula, 1 mark for the whole substitution there, and 1 mark for the final answer, and those are 7 marks. 3, 4, 5, 6, and 7 marks. And then we only have one more question to go through. And this question states, how would the answer on question 5.4.1 change if the angle of inclination is less than 30 degrees? Write increase, decrease, or remain the same, and give a reason for your answer. So what is going to happen here? I want to do this one real quick because now the time is taking long. Okay, so this is going to be 5.4.2. the answer is increase. Increases. That is the answer. And if you say that, obviously you get 1 mark. But now what will happen? The acceleration of the system of blocks decreases. If the angle decreases, the acceleration will decreases. Now, what will be a good option if you are not sure how to do it? Okay, you just can calculate the acceleration and you will see that it decreases. So you just change, you come here and you change this angle here from 30 to 25 for any number smaller than 30, and obviously this one is the same angle, it must be smaller than 30, and you will notice that this acceleration here will be smaller. So this is all for now. It is a really difficult question. It's not that difficult, but long. It's a lot of work. I hope it helped. Try to do it if you have the opportunity, and if you think it helped, thumb up. Thank you for watching, and good luck.